All right, we are now into Chapter 4, Section 4.1, Anti-Differentiation. Just as it sounds, it is basically the opposite direction or the opposite of differentiating or taking derivatives. Now we're going backwards. So our objectives are to find an antiderivative of a function, evaluate indefinite integrals using basic rules of anti-differentiation, and to use initial conditions to determine an antiderivative. So there's a lot of vocabulary involved in the objectives. We've got the term antiderivative, family of functions, constant of integration, indefinite integral, and initial condition to all talk about, and we'll cover all those things as we get there. Okay, so the concept is really basic again. An antiderivative is going backwards. It's basically, if you can call something that you have a derivative, then you can go backwards to find the original function it came from by taking an antiderivative. You actually don't have to have a derivative to start with, but that's just the easiest way to think of it for our initial part here. So let's say that we have f prime of x equals 7x to the 6th minus 3x to the negative 4 plus 1 over x. If you think carefully about each individual term in there, you can probably figure out what the original function was that this came from. 7x to the 6th is probably the easiest one. If you think about it, just kind of piece it together, x to the 7th would have been the original function, because if you take the derivative here of x to the 7th, you're going to get 7x to the 6th. And then the second term, it's a little bit more complex, but again, if you really think about it, you can probably figure it out. The negative 3, x to the negative 4, had to have come from the original function, x to the negative 3. If you were to take the derivative of that, you bring the negative 3 out to the front and reduce it by 1, then you get the negative 3x to the negative 4. And then the last one, you really have to think about, where did I get 1 over x from? Well, if you're remembering correctly, the derivative of the natural log of x is 1 over x. So when we put it all together, it appears that the original function, f of x, would have been x to the 7th plus x to the negative 3 plus the natural log of x. We call that an antiderivative. And notice the word here, an antiderivative. And the reason for that is because what if I were to take this f of x and put plus 5 on the end? Wouldn't the derivative of f of x still be f prime of x, which is what we started with here? It would be the same thing. And that's because the derivative of that 5, which is a constant, is 0. It just goes away. So the general idea behind that is I could put any number here. Instead of a 5, that could have been a 7, or it could have been a negative 13, or it could have been a pi, or it could have been e to the negative 1 power. Anything that's basically a constant could have been put in the place of that 5, and the derivative is still going to get us the f prime of x that we started with. So when we take the antiderivative of something where we don't have any kind of bounds, and this is what's called an indefinite antiderivative, we always add this c on the end, because technically we could have had any function as long as that c is some kind of a constant. What that's called is called the constant of integration, which you'll see right here. So that adding that c is what's called the constant of integration. What that does is it creates a family of functions. Now, if you're really thinking about this graphically, and it's a little bit harder to show here, all that c does, that constant, is going to shift the entire function up and down vertically. That's all that c does. So by putting a plus 5 there, it takes it and shifts it up 5 units. If I was to use the minus 13 that I put up there, it would shift it down 13 units from its original place. That's all. That's what the c does. It creates a family of functions. So every function looks exactly the same. They're all just vertically shifted up and down. All right, so your definition, the antiderivative of f of x is the set of functions capital F of x plus c. I know that's a little confusing. We use the capital letter to indicate an antiderivative of something which is not already notated as a derivative. And you'll notice that the little f of x here was not notated as an f prime, it was just a function. So when you take the antiderivative, you call that capital of whatever the function was. Okay, c is the constant of integration. If capital F of x is an antiderivative of f of x, we can also write this right here, which is what's called an integral symbol. We haven't really dealt with that yet. Your book kind of puts it in a different order. I typically don't introduce the integral symbol just yet, but that's what that is. It's called an integral symbol. It looks like an elongated S. So the integral of f of x dx is denoted by capital F of x plus c, or in other words, when you take the integral, you're really just trying to find the antiderivative. And then since there's no bounds, which we will talk about eventually, you put plus c. So what this says is this integral symbol here tells you it's the command to integrate. It's telling you to do something. The dx out here that you saw in the problem above, it's the variable to be integrated. Technically, the dx is a change of x, and I'll explain to this, I'll get much more in depth with this as we get to the actual application of this when we start talking about areas. And then the expression to be integrated is found in the middle, which in this case was our lowercase f of x. Okay, if two functions, capital F and capital G of x, have the same derivative, then f of x f prime of x and g prime of x then differ only by a constant. So if the derivatives of f of x and g of x are exactly the same, when you take the antiderivative of them, most likely their constant is going to be something different. That's all that that's saying. All right, let's move on. So let's go ahead and see if we can't figure out the antiderivatives of each one of these integrands. The integrand meaning what's inside the integral, the thing you are taking the integral of. So in the first one, I am supposed to be taking the integral of 8 dx. Remember, the integral tells us that we integrate. The dx tells us the variable that we're using. So once we actually take the antiderivative, we're only taking the antiderivative of 8. That's the integrand. So what is the antiderivative of 8? Or basically, what would I have had to have taken the derivative of to get 8? Well, obviously, that would have to come from 8x. You take the derivative of 8x, you get 8. So the antiderivative, or the integral of 8 dx, is 8x. Okay, letter B. I am taking the integral of 3x squared dx. Remember that what I am taking the antiderivative of is the 3x squared. So what would the original function have to have been to give me 3x squared? Well, if I take the derivative of x cubed, that gives us 3x squared. And I am missing something in both of these, and I'm hoping that you caught it. I need to put a plus c on both of these because these are general antiderivatives. I could have had any constant out there that I wanted to. All right, the last one, I am taking the integral of e to the x dx. So once again, the thing that I am taking the antiderivative of is e to the x. The nice thing about e to the x is it is its own antiderivative because it is its own derivative. So e to the x is just e to the x plus some constant c. All right, now there is a part D that I did not do up at the top there because I want to break this one down just a little bit more for you guys. So let's discuss part D. We are given that the function f of x, capital F of x, is the natural log of the absolute value of x. So if we write that as a piecewise function, which is what we see here, that means it's the natural log of x when x is greater than 0. It's undefined when x equals 0. And it's the natural log of negative x when x is less than 0. If we were to take the derivative of that, taking the derivative of each piece in their respective domains, the derivative of the natural log of x is 1 over x. The derivative of something which is undefined is still undefined because you can't take its derivative. The derivative of the natural log of the negative x is 1 over the negative x times the derivative of negative x, which is negative 1, which is what you see here. But 1 over negative x times negative 1 makes both of the negatives positive, so what you end up getting is that f prime of x is 1 over x for all values except at 0. So what that really tells us is that f prime of x is 1 over x, because obviously at 0 that's undefined, so you don't have to include that. So the derivative of the natural log of x, excuse me, the natural log of the absolute value of x is just 1 over x. Okay, the reason that that's important is because now when you take the antiderivative of 1 over x, it's very important that when you go backwards, you include that absolute value there. So when I take the antiderivative of 1 over x, it's the natural log of the absolute value of x, and then plus c. That's the general antiderivative. Okay, that's very, very important. That absolute value will come into play. All right, so here's some of the quick rules. The constant rule. If I am taking an integral of just a constant, which is that k there in there, so if I had 7 or 16 or 42, the antiderivative would just be that constant times x, because if you take the derivative of 42x, it's just 42. So the antiderivative of k is just going to be, whoops, it's just going to be k x, and then don't forget your plus c. The power rule, this is probably the one that we will use most of all. It's very important that you understand this power rule only works with a function where the base is x and it's raised to some constant exponent. Cannot be raised to a function. It's got to be a constant. So like x squared or x to the 2.7 or something like that. The power rule says we raise the power by 1. So keep the base, raise the power by 1. So that's n plus 1. But then you divide by the new power. So you'll divide by n plus 1. It's always the new power, not the old one. And then don't forget plus c. The natural log rule, the integral of 1 over x is going to be the natural log of the absolute value of x plus c. And for x is greater than 0, I really don't like to put this one in there. This is only if you absolutely know that x is greater than 0, then you can write this as just the natural log of x plus c. It is always safer. I strongly suggest you just use this one to keep the absolute value on the x. That way you're not guessing whether the domain is greater than 0 or not. Just stick with the absolute value one. And then the exponential rule. The exponential rule, remember that the antiderivative or the derivative of e to the x is just e to the x. However, if there's something out in front of the x, then we have to include something else. In this case, because what we have in our exponent is ax, that's a linear function. The way we write the antiderivative is still just e to the ax, but we have to actually divide this by a. Instead of dividing, I tend to like to write it as 1 over a, which is the same as dividing. And then don't forget your plus c. So really all you're doing is you're taking the number out in front of the x here, and you're going to make it 1 over out in the front of the e, because you're really just dividing by that number. And again, this is only going to work when this right here, the exponent, is linear. Meaning it's not ax squared or ax cubed or something like that. It's just got to be something x. All right, so there are some of your basic rules. Okay, let's go ahead and put those into action. A couple of real quick notes about the rules of anti-differentiation. Think about the power rule as 2 steps. Again, remember you add 1 to the exponent and then you divide by the new power. Pretty straightforward. And again, this one I don't like to do. This second one here, if you know that x is greater than 0, you're welcome to leave the absolute value bars off of the natural log. Otherwise, it's best to leave them there. I just suggest leaving them there all the time just to make sure you don't make a mistake. Okay, so let's find the integral of x to the 7th dx according to our rules. This is just a regular power rule because it's an x base raised to a constant. So we just simply add 1 to the constant. So that'll be x to the 8th. And then you divide by the new exponent, which is 8, plus c. And that's it. That's your power rule. Okay, in order to do part B, we need to change the square root of x to be a power first. So the first thing I'm going to do is I'm going to rewrite that as x to the 1/2 power. Let's make sure it looks like a 1/2 power dx. Now we can go ahead and use the power rule. Well, if I raise 1/2 by 1, adding 1 to a half now becomes 3/2. So x to the 3/2. And I'm going to divide by the new exponent 3/2. Now, the reason I put this one on there particularly, don't forget plus c, is because I don't like to leave it as something divided by a fraction. That's called a compound fraction. Don't typically like to leave it in that form. So instead of leaving a compound fraction, dividing by a fraction is like multiplying by its reciprocal. So instead of writing as x to the 3/2 divided by 3/2, I'm going to write it as x to the 3/2 times the reciprocal of 3/2, which is 2/3. It's just a much cleaner way of doing it. This is the way you will see me do it from now on. So when I have to divide by a fraction, I'm going to multiply by the reciprocal instead. Okay, in letter C, we need to rewrite this as a power. Now remember that this is not 1 over x, it's 1 over x cubed, so it's not a natural log. Only 1 over x, or 1 over a linear function, will be a natural log antiderivative. So we need to rewrite this. Instead of 1 over x cubed, we can write that as x to the -3 power. And now I can use the power rule. Well, the power rule says to add 1 to the exponent. So that now becomes x to the -2 by adding 1. And then we divide by the new exponent, which is -2. And then plus c. And you could have written that one. You don't have to do this one because that's not a compound fraction, that's just a fraction. But you could have written that one as -1/2 x to the -2 plus c. Or you could have rewritten the x to the -2 as 1 over x squared and then multiplied them out. It's up to you. This is a perfectly acceptable form. Okay, one more example is the integral of e to the 4x. Now remember that this is an e base. This is not an x base. E itself is a constant, so this is an exponential. So we have to use the exponential form, which is actually relatively simple. It just says rewrite it. And then because the 4x is a it's a linear function, we just need to multiply by the reciprocal of the number in the front, which is 1/4. And then don't forget plus c. All right. So again, properties of anti-differentiation are very similar to properties of derivatives. If you have a constant in front of your function, you can pull the constant out to the front. As you see here, we took the constant, we put it out in the front of the integral. Then you can perform the anti-differentiation and then multiply the constant back in. It helps, especially if you're dealing with bigger numbers, sometimes to factor a constant out to the front. Or if you're dealing with exponentials or things like that, so you can pull the constant out to the front. You can't pull out x's, you can't pull out variables that you're actually integrating. The other thing is that you can do is you can add or subtract two different functions, then you can separate the integrals by addition and subtraction. This does not hold for multiplication and division. You cannot separate integrals through multiplication and division this way, but you can separate them through addition and subtraction. Obviously, the order of subtraction matters, the order of addition does not. All right, one more page. We are going to get this all to one video. It's a slightly longer video. I apologize for that, but I think it makes sense just to finish it up here. All right, so let's find each integral. In this case, we are going to assume that x is greater than 0. It's not going to affect anything if we have to do a natural log. I'm still going to include an absolute value. All right, the first one should not be too bad. So 3x to the fifth power plus 7x squared plus 8, that's what we're taking the antiderivative of. So we'll go piece by piece. The antiderivative of 3x to the fifth, well, if we add 1 to the exponent, that now becomes 3x to the sixth, and we now divide that whole thing by the new exponent, which is 6, plus the second one, 7x squared. So we're going to add 1 to the exponent, which is now x cubed, and we're going to divide the whole thing by the new exponent, which is a 3. And then the last one is just a constant, so we know we just put an x onto it. And then we put plus c. Now I'm going to go ahead and simplify this because in the first term I have a 3 over a 6. That does simplify to a half. So I'm going to write that as 1/2 x to the sixth. 7/3 really doesn't simplify. I'm just going to write it as 7/3 x cubed. And then we've just got 8x plus c. That is the general antiderivative for that problem. Okay, in part B, we're going to want to do some simplification here first, because I told you that you can't split this thing up through division. And because I see a division there, I'm like, well, okay, so I don't know how to do this yet. There's got to be another way. What I can do is I can separate all of those fractions and divide each one by x. So really what I'm going to get is an integral of 4 over x plus 3x over x plus 2x to the fourth over x dx. And then I'm going to go ahead and simplify each one of those things to put it in a form that I'm used to seeing. So the 4 I can write as 4 times 1 over x. That helps. The 3x over x, well, the x's are going to cancel out, which leaves just 3. And then the last piece, 2x to the fourth over x, one of the x's is going to divide away, and we're going to get 2x cubed dx. Okay, now all of these are in a position where I can take an antiderivative. So let's go ahead and take the antiderivative piece by piece. So 4 times 1 over x. Well, 1 over x is a natural log when we take the antiderivative. So it's going to be 4 natural log. And it did say that x is greater than 0. I'm still going to include the absolute value around the x. It's just safer. Antiderivative of 3, that's a constant, so it's just 3x. And then the antiderivative of 2x cubed, let's see if you can follow this one. I'm going to raise the exponent by 1, so it'll be x to the fourth. When I then divide by 4, I'm going to get 2 over 4, but that reduces to a half. And then don't forget plus c. Most common mistake I will see people make on these is they will forget the plus c, and it will cost points. Obviously, it is extremely important to have that plus c. Okay, in some cases, you might be given a point called what's an initial condition. What that actually does, if they give you a point, it actually it gives you a way to eliminate the c. It's going to say, okay, I've got all these family of functions, but there's one specific point that I know is on my original, and that's what's given to me, which eliminates the c. It's actually going to tell you exactly how to find the exact function that this came from, not the family of functions, the exact function. So how do we deal with that? Well, we deal with it, we start off the same way. What we do is we find the antiderivative first, including the c. So this is not too hard. We've got an integral, we've got an integral of 2x plus 3. Let's find the antiderivative. The antiderivative of 2x, if we raise the power by 1, that becomes x squared. By dividing the 2 by the 2 gives us 1, so we just get x squared. Plus 3 is a constant, so that's 3x. And then plus c. Well, what that is that's the antiderivative of what we had in there, so we're going to call that f of x. And that's our f of x. That's our general antiderivative. But now what they've done is they've given us this information right here. This right here says that f of 1 is your x value, equals -2. That's your y value, or your f of x value. So we're going to go ahead and plug in 1 where I see all the x's. And then f of x, or y, is -2. That gives us now a way to find c. So let's go ahead and actually solve for c. So we get negative 2 equals 1 plus 3 plus c. 1 plus 3 is 4. If we subtract 4 on both sides, we get negative 6 equals c. So the c value is negative 6. So our final function, our f of x, whoops, I meant to change that color. Our f of x is going to be x squared plus 3x, and then we actually put the c in, which is minus 6. That is using the initial condition. That's what this is. This is the initial condition to find the actual function. All right, one more. We will hopefully keep this under 30. A rock thrown upward at an initial velocity of 50 feet per second from an initial height of 10 feet has a velocity modeled at v of t equals negative 32 plus 50, where t is the number of seconds after the rock is released and v is in feet per second. So I've given you velocity. Velocity was given here. Determine a distance function h as a function of time. In this case, distance is the height of the rock. So if we want to find the distance function or the position function of this thing, we need to take an antiderivative. So let's go ahead and find the antiderivative, because remember, the antiderivative of velocity is the position. So I'm going to call that s of t, because that's typically what we use for position. So the antiderivative of negative 32t is going to be, let's see, it's going to be a t squared, but then we'll divide by 2. So we're going to get negative 16 t squared. Antiderivative of 50, because that's a constant, is just going to be 50t. And then we have plus c. Oh, okay. Well, I guess I should have read my own stuff here more carefully. We're going to call this h, because that's actually what it says in the problem. We're going to determine a distance function h as a function of time. So instead of using s. So we call it h of t, which really just represents the height of the rock. Okay, but this isn't the actual height of the rock, because what we're missing is that c value. But they gave us initial conditions. They said that the initial velocity of 50 feet per second at an initial height of 10 feet has that modeled there. So you might be saying, well, wait a minute, in this equation down here that I came up with h of t, I don't have velocity. You're right. The 50 isn't going to come into play. The 50 is actually only into play right there. It's part of the actual equation. But the 10 does come into play. It says 10 is the initial height. Well, h, of course, is height. So 10 goes in here. The question is, what is time? Well, it does say the initial height, or the initial time. Basically, what that refers to is when time is 0. So when it says the initial, unless it tells you it's a different time, assume that time is 0. So because it says initial, we're going to do negative 16 times 0 squared plus 50 times 0 plus c. Well, anything times 0 is 0, so what we get is that 10 equals c. And what that means is my height equation, h of t, is going to be negative 16t squared plus 50t plus our constant 10. That is the height equation. And then the last part says, find the height and the velocity of the rock after 3 seconds. Well, that's just plugging in 3 into both of these equations. So we're going to get the height at 3 seconds is negative 16 times 3 squared plus 50 times 3 plus 10. And we're going to get the velocity at time 3 is just going to be, using the velocity equation, negative 32 times 3 plus 50. So let's see what we actually get here. And it looks like our height is going to be negative 284 feet. And our velocity is going to be negative 46 feet per second. Okay, and what both of these mean is that we have a negative velocity, meaning it's going down. So I'm assuming that we've thrown this rock off of like the edge of a cliff or something. We threw it up with some kind of an initial height, and then it's falling way down. So the negative 284 feet just means below where we started from. Okay, it doesn't mean it's actually got a negative height compared to like the ground, although something technically could. But in this case, it means that it's gone 284 feet below us, and it's traveling at negative 46 feet per second. All right, just a little over 30 minutes, so that should be plenty enough to do your homework.